And hello, I'm Dr. Priya Hasan. I work at Maulana Azad University in Hyderabad, in India. And very soon, actually, I probably you guys have been informed, but we'll be also having a workshop in your college, which should be in April, 7th and 8th of April, where we'll actually do some hands-on sessions with data analysis. Today it's going to be more of a talk, but hopefully when we meet on 7th and 8th of April, it'll be with Python, as well as it'll be all hands-on sessions where we hope to actually meet you all and do these good hands-on sessions with Python, AstroPy, and various data analysis tools. So today we'll be talking about James Webb Space Telescope and exoplanets, something that's very much in the news, which you must have heard a lot about. So I'm just trying to tell you a few things about it. So what exactly is JWST? James Webb Telescope, in principle, is an infrared space telescope. That's all there is about it. Infrared space telescope. And now we're going to try to understand what does this actually mean. I'm going to start from here. First of all, let's go on to describing, first of all, what was the basic purpose of the telescope? So the idea behind the James Webb Telescope was to be a giant leap forward in our understanding of origins of the universe. Essentially, it basically meant that James Webb was to examine every phase of cosmic history, from the first luminous glows after the Big Bang to the formation of galaxies, stars, planets, and to the evolution of our very own solar system. So if we actually look at what was the Webb journey like, I'll show that to you. So it was, like I said, it's a space telescope. So it was launched, this is in French Guinea, South America. In South America, there's a place called Kourou, where the European Space Agency has its launch site. Okay. Now, all these launch sites are always on the eastern coasts of continents, basically because as the Earth rotates, you launch your satellite, and then what we see is that you have multi-stage rockets, and as the fuel supply, the tanks fall in, they fall into the water. Right? So you typically do this on eastern coasts. So even the Indian launch site is on the eastern coast, right, where we have it, Sriharikota. So here you have the launch of this satellite. It's something very, very interesting because you see, this is the launch. Here are the fuel tanks. So you have multi-stage rockets. What multi-stage rockets do is that these are fuel tanks which are piggybacked on it, and as they get used, they get thrown into, and here they fall straight into the water. So that's why you need to have an eastern coast so that the Earth rotates, and as the Earth rotates, this will fall onto the water. And gradually you see in these multi-stage rockets, various parts of the rocket are shed off. Basically, you want to reduce the weight. You've already used the fuel that was there in these tanks, and you reduce the weight and you drop these things on. So finally you have only the end product. Now look at this. This is something very, very interesting. This telescope is actually a folded telescope. Imagine having a folded telescope. So you have a 6.4 meter telescope which is folded. You can see its parts are these hexagonal pieces which are gold plated. That's why it's even called the golden eye, because gold has very good reflectivity. And you see that this thing gets launched, and it's folded like this. And while you see it, you can see, I'm just checking, you see this is it. Now James Webb finally on its own journey, right? So this is the last piece that went off, and here you have the telescope which has gone off in space. Now this telescope, you see that after it gets launched, what it had to do is it had to open the solar panels. Then this is the sun shield. There's a sun shield which is made up of 5 layers, and this is here, and here you have your telescope sitting on top. The primary mirror is folded up, so that has to open up, but that will open up only after the sun shields open up. So you have, these are the sun shields, which, like I told you, is made up of 5 layers of material, and the telescope is up over here. The primary mirror also gradually opens up, and up here what you can see is the secondary mirror, right? So here you have, this is the secondary mirror coming up, and the primary mirror opens up. So you have this whole sequence of events which have to take place for the telescope launch, right? Okay, now we'll talk more in detail about it, but let's first talk about what's a telescope. A telescope, like I said, is a very simple thing. It's a tool that astronomers use to see faraway objects. So what do you basically have? You have a large lens. The lens does the job of collecting light. It collects light onto a point where it focuses it, and then either you observe at the focal point, or you have an eyepiece where you can actually then observe what is there at the focal point, right? And that's essentially what the job of telescopes you do. So the larger the lens, the bigger the collecting area, and the better you'll be able to observe. right? And the first person to actually use telescopes to look at astronomical objects was Galileo. So here you have an image of Galileo looking up at the skies. But what Galileo, this was a very small telescope. It has an objective lens of just 37 millimeters, right? 3.5 centimeters. It's a small telescope. But what you see is that what Galileo himself observed with the telescope was something so very revolutionary that it actually got him into trouble. You can see an image over here of the church not being very happy of what Galileo discovered. Because what Galileo discovered is, for example, he saw the craters on the moon, right? And the moon was considered to be this heavenly body, which is, a kind of, which is perfect. And suddenly he saw, craters on the moon. He also saw the phases of Venus. Many of you all may not be aware, but Venus actually shows phases, and exactly like the moon. And the only way to explain that is if you were to say that Venus actually it has an inner orbit, an orbit inside the orbit of Earth. Only in that case can Venus have phases, right? Similarly, what he also saw is he saw the satellites of Jupiter. And at that time, this was the times when people believed in the geocentric theory, where the Earth was the center of the universe. And suddenly you have all these objects going around Jupiter, which is yet another object. And therefore, this was it was a kind of a good this thing for the heliocentric theory, which obviously the church did not like. And therefore, what you can see that even with this very small telescope, the kind of things that Galileo actually saw was something very revolutionary, which actually set up a different worldview of the universe. And it was therefore you can actually see that why the use of the telescope or the introduction of telescopes for astronomical observations led to a very large revolution in astronomy. Right. Now, but the other problem with the telescope is that not everything is visible. We know that our eyes are excellent detectors, but they only observe radiation which lies between 3000 to 8000 angstroms, which is basically the visible part of the electromagnetic spectrum, right? You know that all objects, you actually get radiation in the form of the electromagnetic spectrum, which ranges in all wavelengths almost from 0 to infinity. Now, the visible part is a very small window, which you can see of this thing, but you have all this stuff in other wavelengths. And the problem is that if you use a plain optical telescope like the one that Galileo used, you are only observing a small fraction of the electromagnetic spectrum. You need to observe other parts because different physical processes. For example, if you have black holes, they are going to radiate at very high energy, for example, in X-rays and gamma rays. For example, if you have very young stars or you have exoplanets, which we are going to talk about today, they are going to emit in the infrared because they are colder objects. And therefore, what happens is we actually need to have a telescope which lets us look into other parts of the electromagnetic spectrum, because depending upon the physical processes we are interested in, we need to look at those parts of the electromagnetic spectrum, right? And therefore, and the other problem we have about the electromagnetic spectrum, not just our eyes, is our atmosphere. Now, the atmosphere we have is obviously life-giving. It gives us oxygen, it gives us water, it gives us all the things essential for life. But the problem with the atmosphere, it forms a blanket on the earth, and it actually does not permit all radiation to pass through it. So we can actually thank our stars that it does not let in X-ray ultraviolet radiation, because otherwise that would burn us off. We could not have survived if we had X-ray ultraviolet radiation. It only permits the visible part of the radiation, some windows in the infrared, and a very large window, which is the radio window, which is what we use for communications, because you have such a large window which is completely transparent for the atmosphere. But the problem is that these part of the electromagnetic spectrum do not pass through our atmosphere. And therefore what happens, the other problem of our atmosphere is that the atmosphere actually has turbulence. So what you look over here in this image, you can see that I have a star which I'm looking at over here. But because there's turbulence in the atmosphere, right, I will try to show that to you again. Because there's turbulence in the atmosphere, what happens is that you can see that there's a shift in the position of a star because of the turbulence in the atmosphere. You can see that over here also, that the star gets shifted. And this causes what is called seeing. That means you see a blurred image of the star instead of seeing a sharp image. But if you go, for example, on a mountain top, then there's lesser atmosphere and there'll be lesser shifting of this, due to which you'll be able to see better. And therefore, we try to keep telescopes on mountain tops where it is high and preferably dry, so that you can actually see the the thing well. And this is what we call resolution. So, for example, a badly resolved image is this. This is a badly resolved image where you have a smudging, you have a blurring of images caused because of the atmosphere, turbulence of the atmosphere, etc. But if you did not have an atmosphere, or you could correct it in some way, you will see something much more sharper, like this image, or for example, this image, right? Or you can see here, you can see much sharper images. So that is another problem which happens because of our atmosphere. Number one, it blocks out radiation, and number two, it actually has turbulence, which actually blurs our images. What we see of the sky gets blurred. A light itself is a wave, and therefore light shows diffraction, and because of diffraction itself smudges the light, right? So for example, if I have a point source of light, you have a diffraction pattern which shows you how the light from that point source gets spread, right? It gets spread like this, and we actually see this smudged effect, right? If these two objects are close enough, then what will happen is you will see them unresolved. They will appear as a single object which is broad, right? If, for example, they satisfy what is called the Rayleigh criterion, then you can resolve them and see them as two objects. But they are spread out, right? These are spread out images. This happens because of diffraction and because light is a wave. But this is something which we cannot anyway do anything about, because we cannot change the nature of light. Light anyway has its wave nature. It's going to do this. Now, infrared wavelengths are basically what we are interested in, which do not pass through our atmosphere. If you remember, I said JWST is a space infrared telescope. So this tells us that we want to actually observe in infrared, but we know that our atmosphere has only windows in infrared. It does not permit all of infrared light. And therefore, if I want to actually observe with the infrared, I need to go out of the atmosphere. Infrared wavelengths were discovered by Herschel in 1800, and they are typically the emission which comes out from you and me, cold objects. We are cold objects, and we emit very well in the infrared, right? So therefore, what happens is, it becomes necessary for us to send our telescope in space, right? So like I told you, the whole idea of going out in space is basically because, number one, you cannot see all emissions in all wavelengths. They are blocked by our atmosphere, as well as you have the effect of the atmosphere, which is the seeing effect, which actually causes images to get blurred. And like I mentioned, so you will have diffraction limited seeing, but by going out to space, you can actually look through these other parts of the atmosphere, which otherwise would have got, blurred. Okay, and the other problem is that ground-based telescopes, they have limited observing time because of the Earth's rotation, and therefore, what happens if you have your telescope out in space? The space telescope will anyway let you observe, irrespective of the time, date or night time. So you can actually have 24/7 observations, which you can have if you have a space-based telescope, right? And, I'm sorry, there's some disturbance which is caused, and that's basically because of the, 1 minute. Sorry, I'm sorry. Okay. 1 minute, I'm sorry. Yeah, okay. I'm sorry. Okay. So these are basically the advantage of sending out your telescope in space, right? And that's exactly why you need to send the James Webb Telescope to space, right? And right. But there are disadvantages of sending space-based telescopes, and the basic problem with sending a space-based telescope is that they are much more expensive, right? You know that the James Webb Telescope has costed $11 billion. That's the cost of the James Webb Telescope, and also because of their location, they are out in space. They are very difficult to maintain. And the Hubble Space Telescope is actually at a height of only about 550 kilometers. It's very close by. So probably it's closer between Hyderabad and Nagpur. And that is why there were various service missions which were done to the Hubble Space Telescope. But in the case of this thing, in the case of James Webb is at a much larger distance. It's at a distance of 1.5 million kilometers, and therefore it's not exactly possible for us to actually have any kind of servicing missions, right, for the James Webb telescope, which actually is what creates a problem, right? Okay. Now there have been various space telescopes which have actually been sent out in space, and you can actually see an image of them. You may have heard about somewhere of them. There's SOHO, which observes the sun. There is the Hubble Space Telescope. There's the Integral, Skylab. There have been various. So there's been a good amount of experience which people actually have on sending space-based telescopes, right? And obviously space is out of this world. This is an image of the Hubble Space Telescope. It's the most well-known space telescope. So it was launched with the space shuttle, and it is still operational. It is one of the most effective, useful space telescopes we've ever had, the Hubble Space Telescope, right? And one of the other well-known space telescopes is the Chandra X-ray telescope. Now, this is named after Subramaniam Chandrasekhar, and what you actually have is, I'm sorry. So what you actually have is, like I showed you, the atmosphere totally blocks off radiation which comes from the in X-ray radiation, and therefore if you want to observe an X-ray, you have to go out in space. The Chandra X-ray telescope is still operational. It was launched by the space shuttle. It's still operational, and it still has given us very, very good data, right? Spitzer is an infrared telescope, also very effective. It's about 0.85 meters. It has also given very good data. There's Herschel. This is a 3.5 meter telescope which observes in the far infrared, the mid infrared, and the far infrared. It is no longer operational, but it has given us very good data. The Hubble Space Telescope is what we spoke about. It's about 2.4 meters in size. It has various cameras and spectrographs on it, which have been given very good data. We don't have too much of time, but I'll try to show you some of I'm sure you have seen many of the images which have been obtained using the Hubble Space Telescope. This gives you excellent resolution. Like I told you, because you're out in space, you don't have the atmospheric effects, and therefore you can actually look out, right? So here you can see, I'm showing you a few of the Hubble. These are all HST images, which you can see are totally mind-blowing, basically because of the accuracy you get of sending a telescope in space. It's very important for us to know so that we can appreciate the advantage we have of James Webb actually being out in space, because of the kind of data and the kind of images you can actually get. See, these are all Hubble images, which are excellent. They are they are by far the best you can get. Okay. Now, what's the difference between Hubble and James Webb? Hubble is a 2.5 meter. This one is 6.4 meter. So the James Webb is much larger, obviously. And but the idea of James Webb was to actually look for origins, right? And if you want to look back at origins, we just say that it's very essential that you look in the infrared. I'll tell you in a minute why is that important. So it was decided to have a 6.5 meter diameter, observe in the infrared. I'll explain to you why in a short while. And basically the idea was that if you want to look at the origin of the universe, you basically need to see galaxies which are very, very far away from us. Okay, and they also wanted to look at young stars, young planetary systems, exoplanets. Again, these would be observable in the infrared. And this obviously came at a very great cost. This is 10 billion, but actually it costed $11 billion, because the launch itself costed $1 billion, and the making of the telescope was 10 billion. So you had the United States, Europe, and the Canadian, that is the European Space Agency and the Canadian Space Agency. They all three got together to build the telescope. Now, often people say that James Webb is a successor to Hubble, but in principle it is not, because actually it is the Hubble Space Telescope is an optical telescope. It looks a little bit in the ultraviolet, a little bit in the near infrared, but the James Webb is a purely infrared telescope. It does not look in the optical, and therefore the James Webb in principle is a successor, probably more to Spitzer, which we spoke about, rather than to the Hubble Space Telescope. So, you all are engineering students. So, in the end, I'm even going to talk to you all about what can engineers do in astronomy if they are interested. And you can see that the James Webb is a pure engineering exercise. Building the telescope is a full job of engineers, and therefore, in astronomy, you have a very important role played by engineers. One is the building of the instruments. Like I'll show you how building all these instruments is very, very complicated. Hello? Is there another sound coming? No, no, but there's some other, there's another sound coming. 1 minute, huh? Yeah. Okay, okay. No, no, no. Actually, from my browser, some video started. It's not yours. It was my problem. Don't worry. Okay, no problem. So, in short, what I wanted to say, since all are engineering students, I will describe to you how each part of the telescope is actually an engineering job, an engineering effort. Okay. So, we'll first talk about the mirror, the sunshade, etc., and everything. So, if you see the mirror, Vedant, you can hear, right, properly? If you see the mirror is a 6.4 meter mirror, right? Now, the Hubble mirror was only 2.4 meters, and therefore it was made up of a single piece of glass. But the case of the James Webb is that because you cannot build a 6.4 meter telescope so easily, right? Therefore, what happens is this was made in the form of hexagonal pieces, right? So you have these 18 hexagonal pieces which are put together, and together they make up the telescope, right? Now, how do they make these pieces? So if you see, Hubble's telescope is only at a height of about 570 kilometers, right? While James Webb is 1.5 million kilometers. It had to be sent away so far. So it almost spent a month to travel from the Earth to this point, which is called the L2 point, the Lagrange point 2. The mirror, like I told you, is made up of 18 segments, right, with a diameter of 6.5 meters. And since it is being sent at such a large distance away, it is impossible for us to service this telescope. Okay, 1 minute. I'll just. Okay. Yeah, so I think there was some problem. I'll just come back. It's the net issues. It comes and goes. Okay. I hope now everything's fine. Hello, is everything fine now? Vedant? Hello? Is it fine now? Okay. So, we were comparing James Webb to Hubble. There's an echo coming. Fine. So, we were comparing James Webb to Hubble. Well, I told you that James Webb being much larger is... Okay. You're not getting an echo? Are you getting an echo? Hello, are you getting an echo? I don't know why the echo is there. 1 minute. Should I exit and come in again? I wonder whether that... okay, am I doubly connected? Okay, I'm doubly connected. That's why. Now it's fine? You can see my image also? You can see the PPT properly? It's all fine? The PPT is fine? Okay, good. No, no, I was doubly logged in. I got logged out from one and got in. That's why. Okay. So we said that the basic difference between James Webb and Hubble is at a distance of only 570 kilometers, very close by. But James Webb was sent to 1.5 million kilometers. This had to be done because James Webb is an infrared telescope and the Earth itself is a very good infrared emitter. And therefore, you need to send it to a distance far away from the Earth. Otherwise, it will get totally saturated by the emission from the Earth. And this point which it was sent, we'll talk about it in a bit, is called the Lagrange point, the L2 point. And this is at a distance of 1.5 million kilometers, therefore making it impossible for us to service the telescope at any point of time. Unlike what we did for Hubble. Hubble was serviced 5 times, basically because it's not too far away, right? The other thing is that James Webb is much, much larger than Hubble. So it's made up of these 18 segments, and all of them together make up the telescope, right? So it makes it a little bit more, it makes it much more complicated thing. Now, to explain the infrared part, I'm going to now talk to you a little bit about Hubble and the expanding universe. Many of you all may have heard of the Doppler effect. What is the Doppler effect? The Doppler effect states that if you have a source of light which is moving away from you, its wavelength, the emission, the radiation wavelength actually shifts. So if that source of light is moving away from you, like you can see over here, then it moves towards the red region of the spectrum to longer wavelengths. While it's moving towards you, it moves to shorter wavelengths, which is called blue shifted and red shifted. So what Hubble did was basically, he observed, this is the Mount Wilson telescope, he observed the spectra of galaxies. And when he observed the spectra of galaxies, he saw that they were red shifted, right? That means these galaxies seem to be moving away from us based on the Doppler effect. So what he did is he observed the spectra, and there's a simple formula, delta lambda by lambda is equal to v by c, which can help you calculate the velocity with which these galaxies are moving away from us, right? So he measured the velocity with which these galaxies are moving away from us. He also observed what are called Cepheids. Cepheids are pulsating variables which are found in various galaxies, which can be used to actually find out the distances to galaxies. So what Hubble did is he put these two things together, and he got the velocities from the Doppler shifts, he got the distances from the Cepheid variables, and he discovered that the velocity of galaxies was directly proportional to their distance from us. So what happens is, if you have a galaxy which is close to us, it seems to be going at a smaller velocity, while if there's a galaxy further away from us, it seems to be moving with a larger velocity, right? And therefore this is what is Hubble's law, which is V is equal to h naught into d. Now, if you try to picturize this basically means that if you were standing over here, these galaxies are moving away from you with a smaller velocity, these ones are moving with a larger velocity. If I were to play this movie in the reverse, right, all these galaxies would come back to the same point, right? And as they would come to the same point, right, later on the expansion starts. So what happens is, it actually gave us the theory of the expanding universe, where you have all the galaxies put at a certain point, and then the Big Bang took place, after which all these galaxies expanded and moved away from us, right? So this is the very most important observational evidence which we have of the expansion of the universe, or the Big Bang, which is what Hubble discovered, right? And therefore what happens is, I don't know why, right? And therefore, what happens is, this is what the spectra of galaxies look like. I don't want to scare you, but basically it means that Z is the redshift. If you have a spectral line coming somewhere over here, as the distance to the galaxy increases, that means as the redshift increases, the same spectral lines goes to the redder part of the spectrum, right? So instead of seeing it, supposing it was an optical light, you will now see it in the infrared part, because the infrared part is the longer wavelengths, right? And therefore that gives us our justification. Why do we need to actually look in the infrared part of the spectrum? Because the spectrum lines which would have come from a galaxy in the optical part of a spectrum, because this galaxy is far away from us, the spectral line gets Doppler shifted to the redder part of the spectrum, and therefore it would be observable only in the infrared part and not in the optical part. And therefore, if you want to look at distant galaxies, that is galaxies which are far away from us, which belong to the early universe, when you are at the origin of the universe, then you would have to look for it in infrared. You cannot look for it in optical, right? That's the very basis. So that is the justification of why do we need an infrared telescope. We need an infrared telescope because distant galaxies are going to emit in the infrared part of the spectrum, right? We will not see those lines in the optical path, and only we can observe them only in the infrared part. And the idea was to basically study origin of the universe. If you're studying the origin of the universe, you need to look at very distant galaxies, that is galaxies which were present at the time of formation of the universe, and therefore you would have to look in the infrared, right? And so in principle, when you're looking, because time has a finite speed of light, the more distant you look in the universe, the more early universe are you looking at, right? So it's a kind of a time machine. So for example, if I'm looking at the sun is 8 light minutes away from me. So I'm actually seeing the sun as it was 8 minutes ago. The moon is about 3 light seconds away from me. So I'm actually seeing the moon as it was 3 seconds ago. So if the sun were to switch off, I would know that only after 8 minutes, that is when the light stops coming from it, right? But it's, in principle, as I look at objects, supposing if it is about 4 light years away from me, I'm seeing the object 4 light years ago, right? I'm seeing it as it was 4 years ago. So if you want to actually look at the early universe, you basically need to look at distant objects. And these distant objects are the ones which are going to be observable only in the infrared, right? And therefore you basically need to look in the infrared to see these very distant objects, to see the universe as it was at a very young age, right? So that is what we call looking back into the cosmos. So as we are looking in our modern universe, this is the present universe, I'm looking back, I look at distant objects, and by looking at distant objects, I can reach to a part which is closer to the Big Bang. The Big Bang is the point of formation of the universe, right? What I told you, expanding universe, they have the galaxies moving away from each other. But the Big Bang, it started, and as I'm looking deeper, further and further away, I'm reaching a stage which is closer to the formation of the universe. So with Hubble Space Telescope, we can come to a distance of about this when the universe was about 1 billion years old. But now with James Webb, we are coming to a period when the universe was barely like 300 million years old or 100 million from the Big Bang, right? This earlier part we cannot observe because this period is not the period when you had stars and galaxies. So you're not going to be observing anything over here. These are observed by other things. For example, the Kobe satellite, the WMAP, they are looking at these earlier parts. But if you want to look at this in with observations, you can go back. So that's what basically James Webb is doing. It's taking you way back in time when you're seeing the universe when it was barely like a few million, 100 million years old, right? So as you go on to redshift, as you increase the redshift, you're seeing the universe as it was earlier and earlier, right? The age of the universe is about 13.7 billion years old. So as you're increasing your redshift, you're going to be able to see the universe as it was, earlier, in an earlier stage. So like I showed you, there are various probes. Ground-based observatories barely go to 6 billion years, age of the universe. Hubble goes to about 1 billion years, but now with James Webb, we are going to about 200 million years. So we are seeing the universe as it was when it was only 200 million years old, right? And we get to see all this period. So you can actually see the evolution of these objects right from the period of 200 million years age till present times. That's the basic purpose, right? So you can actually see the evolution, for example, of galaxies, of stars, etc., from those early times to present times. So that actually now I can sum up why do we want to look in the infrared. So the infrared lets me actually look at this. The other big advantage of the infrared is you can see in this image. This is the Orion constellation, which many of you would know about. This has a lot of young star forms being formed over there. If you look in the optical, it looks black. You don't see much because there's lots of gas and dust over here. But this is an image, a Herschel image of the same region where you can see so much of gas and dust, and you can actually see how is star formation taking place. Like you can see these rings of gas, you can see all this area with gas and dust showing you how star formation is taking place. So now what happens is if you want to look at young stars, star formation, and star formation is very closely related to planet formation, how are planets formed, again you'll need to look at dusty parts. If you're looking in dusty parts, you have to look in infrared. And therefore it was decided that James Webb has to be an infrared telescope in space because it wants to look at the formation of stars, dusty regions where stars are formed, where planets are formed, even galaxies form in such regions, as well as look at very young galaxies right in the beginning of the universe, again which you'll have to observe only in the infrared. And therefore it was 100% required that you observe in infrared. But because he wanted to observe in infrared and because the Earth is a very good infrared emitter, it became very essential to send the James Webb very far away. And therefore, James Webb was sent away to a distance of 1.5 billion kilometers, right? Because it's so very far away, right? And you won't have contamination or light coming from the Earth over there, right? So, like I said, we've already compared Hubble and James Webb, and this thing. Hubble operates at a temperature of barely 20 degrees, so therefore it has a very long lifetime. The problem with James Webb is that because it's an infrared telescope, and the rest, the Earth, etc., emits a lot in the infrared, we need to cool the telescope. And because we need to cool the telescope, you have cryogenic technology being used, and therefore the material being used to cool it gets finished at a certain point of time. It has to operate at a temperature of minus 230 degrees centigrade, and therefore the lifetime of James Webb is going to be barely 10 years. It's not going to last as long as Hubble. Hubble is still operational. It was launched in 1990, but it's still very much operational after 32 years. So in principle, James Webb is a Herschel complementary. So like I told you that this is the mirrors of the telescope made up of 18 segments, right? And these 18 segments had to be separately manufactured in a cryogenic vacuum. And what's basically done is that they are cut in a honeycomb structure. Okay, you have these pieces, and these pieces are all placed together. Below them you have, you'll see that in the video I'll show you. This is the making of this thing. Below them you have what are called accentuators. Okay, those accentuators help keep the shape of the mirror. So you have accentuators below the mirror, and those accentuators help to actually align these pieces so that together they sum up and act as a perfect mirror, right? So we can actually see those accentuators. I'll show that to you over here. In the video you can see. So here you can see this is your 18 segments. Together they have got to make up a single mirror, right? These are the separate pieces, gold coated. And what you have, these are the accentuators. These are placed below the mirrors, okay? So you have this hexagonal piece. On top of that you have these accentuators placed, and the basic point of this is basically to align the segments. You have to align it to a fraction of a wavelength of light, so perfectly aligned, so that together they can give you the effect of a single mirror, right? So you actually align them in that kind of a perfect way. And 3 months of the first 3 months of the James Webb telescope was basically used in aligning this, because otherwise each of the 18 segments is going to give you a separate image. What we have to do is we've got to align the mirrors so that all the segments give the image at the same point, the same central point. And like I said, the first 3 months of the James Webb was basically used in actually aligning these mirrors, right? So this is the segment. There's also a secondary mirror, tertiary mirror, and steering mirrors. So if you actually see how does a light beam fall onto the telescope, this is the primary thing, this is the secondary mirror, tertiary mirror there. So you have the light coming in on here. The mirror focuses it like it's supposed to do it, focuses it, sends it to the secondary mirror. From the secondary mirror, it's turned on to the tertiary mirror, and then from there it's sent to the various different instruments which are present on the telescope, right? So now, because this is an infrared telescope, we want to protect it from the sun rays as well as the earth rays, and therefore there is a 5-layer sun shield. Okay, so this sun shield is actually made from a special material, a polymeramide film called dew point, and these membranes are specially coated with aluminium and a doped silicon, and this actually forms a very perfect kind of a sun shield. This is almost the size of a tennis court. It's huge. And actually what happened in 2018, there was a tear in one of the parts, and therefore that actually delayed in the delay of the launch of the telescope, because the sun shield part of it had to be remanufactured because of this thing. So this will actually help the telescope be at this very important temperature of minus 230 degrees centigrade, right? It has to be barely 30 degrees above absolute zero, 30-40 degrees. We want it to be that cold. And therefore you actually send it so far away, as well as you have the sun shield. So when the launch took place, the sun shield was folded. After the launch took place, then the sun shield had to be opened up, right? And all this has to be done very perfectly. There are no two chances. It has to happen in the very first chance. You're not going to get an option to actually do it again. So all these things had to be very perfectly tested so that immediately the whole thing will work, right? So it's about 20 meters across, it's huge, so that it properly protects the telescope from any kind of radiation. And like I said, all this happened in an automated manner in a very perfect way. Now, the other important thing is where exactly is the telescope? Like I told you, the Earth is a very good emitter of near infrared, so is the Sun, or infrared. And therefore, there are 5 points in the Earth Sun orbit which are called the Lagrange points. These are the points at which the gravitational force between the Earth and the Sun are perfectly balanced. So this is an ideal place for you to put a satellite because you would not need any energy to maintain its position. It will stay over there because that's a point where the gravitational forces, everything is balanced. So therefore, L1 point is the point which actually faces the Sun. So for example, the Aditya mission, which is very soon going to be launched to observe the Sun, will be at the L1 point. The L2 point is on the other side. So what happens, L2 point will never look at the Sun, and therefore it's always shielded. So that is exactly where James Webb is, at the L2 point. So you have the Earth going around the Sun. This is the L2 point, and this takes an orbit which is going around the L2 point. Okay. So typically, because of that, the Earth, the James Webb telescope will never ever face the Sun. Right? We want it to be totally shielded from the Sun, so that you will never get any emission coming from there. Right? And therefore, the Webb is about 1.5 million kilometers away from the Earth. So if you want to actually check where is Webb, if you look at the crescent moon, the opposite side is the side where the Sun is, and therefore the Webb has to be somewhere here. It's always in the opposite direction of the Sun, right? Because it has been, the orbit has been planned in such a way that it never faces the Sun. Now the instruments on the telescope, there's a near infrared telescope camera, there's a MIRI instrument, mid-infrared, and there's a fight guidance sensor, and there's also a spectrograph, a near infrared spectrograph, which is there onto the telescope, and all of them together give you great value to see. Like you look at this, what I was telling you earlier also, that it's a pure engineering feat. There are a lot of engineers who actually go into the instrument building of how does the instrument have to get built based on the specifications given by the astronomers, right? They say this is what we want your instrument to be doing, but then the engineers have to actually make the instrument, right? For example, even the ISRO, the Indian Space Research Organization, is basically made up of engineers. It's not made up of astronomers, but it's made up of engineers, because they are the ones who actually make all the stuff that goes into the satellites. So it's a pure engineering wonder. If you actually see, you can actually see how every part of it is actually done by engineers. Obviously, it's not done by astronomers. It's all done by engineers with a perfection that is required. Right? I won't do this. Let me run through this. So once it was completely tested, right? This was done at the Goddard Space Center. What you then had is that the whole thing had to be packed up. You see the telescope is being packed up. You fold the primary mirror. This is the sun shield. The sun shield was also folded up, put into that thing, right? This is the sun shield. And then you also have the solar panels, right, which is the source of energy for the thing. So you have to actually add these things all up together. And after it gets launched, the whole thing has to open up, right? And like I mentioned, this has to be opened up in pure perfection without any mistakes, because there is no second chance, right? You're not going to get any second chance to do anything. Now, after the whole telescope was kind of, packed up, it was then sent off on a barge, right? This is the barge in which it was sent. It actually did a 16-day journey to French Guiana, right, in Kourou, where you actually had the launch of the telescope taking place. So once it was launched, it had to go to this L1 point, which is 1.5 million kilometers. But immediately after launch, first of all, you had the solar panels to be deployed, the antennas to be deployed, the sun shield, and you had the telescope to open up, and that's when it reached the L2 point. So before it reached, all these things had to happen. You had the sun shield to open up, the 18 segments, cameras had to be cooled, and all this took place. This took about 6 months, the whole process. And only after that was the whole thing done, right? And so this is the last view we have the James Webb when it was actually launched. Now I have only little time. We'll run up to exoplanets. I'll have to hurry through that. Now, one of the first, the James Webb first year of science is scheduled from July 2022 to June 23. And the cycle one, about quarter of the time, is actually being devoted to observations of exoplanets, essentially exoplanet atmospheres. Now, what are exoplanets? It's a planet outside the solar system. So, first step is actually to look for exoplanets. And why do we look for exoplanets? I love this argument which was given by Carl Sagan, where in the book as well as in the movie, this was the justification while Carl Sagan gave why do we need to look for exoplanets or look for life in the universe, is that the universe is a pretty big place. If it's just us, seems like an awful waste of space. And this was the very simple argument Carl Sagan did as to why do we actually need to look for life in the universe, and starting off with that with exoplanets. So you first of all you look for exoplanets, then you look for habitability, and then you look for life, right? So that was the argument given by him. Now there are various planet detection methods which are used. Some of them are dynamical, of which the most popular one is the radial velocity method. You actually see the radial velocities of stars. There's another method which is called microlensing. You will get an effect in the light curve of the stars. Then with photometry, what is most popularly used is what is called transit photometry. So there are various kinds of methods which are actually used to actually look for exoplanets. So I have them mentioned over here. One is the radial velocity method, microlensing, transit photometry, direct imaging. But you have to always keep in mind that looking for exoplanets is literally like finding a needle in a haystack. It's a very, very difficult job. It's absolutely not easy. And therefore, all these techniques have been used. If you see that here, there's a very big peak of the transit method being used for detection of exoplanets. And that's basically because of the launch of the Kepler satellite. The Kepler satellite was a satellite which was detected to actually look for exoplanets using the transit method. And therefore, you can see that earlier, a lot of contribution is there from the radial velocity method, the red part. But there's a very, very large contribution coming from transits, essentially because of the Kepler as well as the TESS satellites. The other ones are microlensing imaging, which have their limitations, so you do not have too many detections using that. Now, what's the radial velocity method? The radial velocity method is that if you have a star with a planet going around it, right, you're going to have a wobble. Wobble, why? Because together they are going to go around their common center of mass, right? They're going to go around the center of mass of this system, due to which the star's position will wobble. And because the star's position will wobble, the radial velocity is the velocity of the star in our line of sight, right? So if you're going to get a spectrum from the star, you're actually going to get a slight shift, which will come because of the movement. So it's going to get red shifted as well as blue shifted, and with that you can actually measure the radial velocity. So that's the radial velocity method. This was a very popular method which was used. So it's explained again over here. So if I have a spectral line, this is the star. You can see the star is coming and it's going, due to which the spectral lines are getting shifted to the red part, longer wavelengths, and then to the blue part, depending on whether the star is going away from you or whether it's coming towards you, right? You will have a different shift in the thing. So you'll actually measure this wobble. Now, this was a method which was used by the Geneva team, and in this case, you can actually measure, for example, Jupiter. If you were to actually observe our solar system from a distance, Jupiter would actually cause a difference in velocities of about 13 meters per second. Earth causes a very small difference in velocity, only 0.1 meters per second. And but for example, the HARPS instrument, this is on the VLT in ESO, you can measure a limit of about 1 meter per second. And therefore, with the HARPS instrument spectrograph, you can actually measure Jupiter-like like planets which have these kind of variations, right? And this is exactly what was done by a group. But obviously there's a problem that depending on the tilt of the exoplanet, you will actually only see the projection of the velocities, and you will only see what is called the V sin I, right? V into sin I, where I is the inclination of the orbit. You are going to see the effect of only that in your observations, right? Which is the sin I part. So initially, the first discovery of an exoplanet was made not around a main sequence star, but around a neutron star, okay, using what was called the method called pulsar timing. That can also be, there's a difference in the pulsar timing because of the presence of this thing. But the first exoplanet around a sun-like star was observed with using 51 Peg. This is a star, and this was observed by the radial velocity method by Michel Mayor and Didier Colletz in 1995, and this is exactly for which they got the Nobel Prize in the year 2019. This is the group. This is the PhD student Didier, who is a student of Michel Mayor, and they observed this first confirmation of an exoplanet using radial velocity method. So the star was a sun-like star, and probably that's why the pulsar detection was not given a Nobel, but the one in this case was given because the star itself, the host star, was a sun-like star. And you can actually measure this thing. The radial velocity divided by c is equal to delta lambda by lambda, and therefore you need a very good resolution for your spectrograph so that you can actually observe this, right? Obviously, with radial velocity, there could be disadvantages. You can have wrong detections. You could have a shift happening because of some other reason. The planet could be wobbling because of some other reason. Could be magnetic fields, could be stellar activity. You could get false signals because it's basically a broadening of the spectral line. So there are various ways to actually rule out false positives and actually try to this thing. So that was a very big job for this group from Geneva, which had to prove that the velocities they were getting were because of the presence of the planet and not because of something else. The other standard method used is what is called the transit method. This is the method used by Kepler as well as TESS. So when you can actually see that if you have a star coming in front of a planet coming in front of the star, there's going to be a fall in brightness of the star. So this is what is called the light curve. The light curve is the difference in brightness with time, and you'll get a small difference in that when the transit takes place, right? So obviously this depth of this transit is the ratio of the squares of the radius of the planet to the star. Now we know that the Earth's radius itself is very, very small compared to the Sun's radius, and therefore if you were to make such a radius ratio for the Sun and the Earth, take radius of the Earth square divided by radius of the Sun square, you'd get a factor of 10 power 4. And therefore your photometry, this dip, right, this dip, it makes it look a little big, but actually it's something very, very small. It's a 1% difference in the dip, right, or rather 0.1% which you're going to get. So it's like you have 1,000 light bulbs and one light bulb goes off. How do you actually detect that? The other method used is called the micro-lensing method. So in this method, what happens is that if this is your star and there's a planet coming in front of it, because of the gravitational influence of that, you will get a change in the light curve. But this is obviously a very difficult thing to observe. It's a 1 in a million case, but it's still a worth it method of actually trying to observe and detect an exoplanet. The fourth or the last method which is there for detecting exoplanet is what is called direct imaging. So for example, you have a star here and it has 3 planets. You want to observe the star. It's obviously very difficult to observe because the star is going to be much, much brighter than the planet. And therefore, if you want to actually do that, that's very, very difficult because often the planet is close to the star is so bright, and you won't be able to observe it. So what is the way around the problem? The simplest way is what is called a coronagraph. So for example, when we look at, this is an image of the sun. So if you were to actually look at the sun has a very hot corona outside it. If you were to look at it directly, you will not see the corona because the sun itself is so bright. And therefore what we do is we actually put something called a coronagraph, which actually blocks the light from the sun so that we see the corona. Now nature also does this, which does it in the form of what is called a solar eclipse. So in a solar eclipse, what happens? The moon comes in front of the sun, it blocks the light coming from the sun, right? And we can see the corona of the sun, which we call the butterfly effect, the diamond ring effect, these various effects which come because the moon blocks the light from the sun and you can see the outer region of the sun. So essentially what you need to have is a coronagraph which can block the light from the star. If you can block the light from the star, then you can see the images of the planets. So in this case, that's what's done. The starlight has been blocked and you can look at the planets, right, which are there around it. So, this is a movie. So what happens is you have this object over here. I cover it up and wow, here you get to see the planet. So you could not see the planet in the beginning, but because I actually moved this thing, the coronagraph, that's when you actually get to see the planet. See, there's a planet sitting over here, which in general you can't see because present a star, but you see it if you put the coronagraph. So direct imaging has been done using the Keck telescopes, with which people have actually discovered planets around stars. I don't have the time to do that, but there are various examples of this being done successfully. Beta Pictoris also was imaged like this. You had to near infrared telescopes with you had to do near infrared images with a very large telescope with which they actually managed to observe. Now, like I told you, Webb, the plan was to actually observe exoplanets. So Webb actually gave out its very first images. There were 5 images, which were the first light images given out with Webb, right? And in this case, this is an image of an exoplanet, which Webb this thing, in the infrared using the NIRCam. It has near infrared camera, and what it actually did is actually it gave images. You can see the planets over here, right? You can see the planets over here. You can see them over here also. It has actually got images of these planets, which you can see in this case. So what can James Webb basically do? It's very difficult for James Webb to actually image planets, because planets are very faint, stars are very bright, and it's on the easier part for James Webb is to study exoplanet atmospheres using its spectrograph. So it can actually see water. It can check planets where you have water. It can also see various planets where you have, for example, carbon dioxide, or you have other kind of elements. And for example, if it detects methane, methane is considered as a biosignature or a typical element which comes out when you have life on or habitable worlds, and that's the kind of job that James Webb can do. So in the first light images of James Webb, it basically observed this exoplanet called WAP 96b. This is not an image from Webb, but this is showing you the transit of it, where you can actually see the fall in brightness, what it did. What Webb did is it actually observed this star system for 6 hours 23 minutes, 2.5 hours before the transit, 1.5 hours after the transit, and when the transit. So basically what it does is it uses that period to actually, before the transit, it observes the spectrum coming from the planet as well as the star. Then when it sees it from here, it actually sees